Welcome to the introduction to data management for machine learning and AI. In today's session, we will talk about databases, data models, and schemas. Databases and the systems managing them are central to data management tasks. To start with this topic, let's informally define some terms. What is a database? Simply said, a database is just a collection of related data. To expand on this, a useful database would adhere to a selected data model and would also have one defined data schema. A database management system, or DBMS, is a software system which manages and maintains a database. Such systems can fulfill many tasks ranging from storing data, querying data, securing data, and making sure that multiple users can concurrently access and modify data without messing anything up. Most databases used in critical scenarios would, of course, rely on the services of a database management system for reliability and efficiency. However, we can also imagine unmanaged databases, such that as just collection of data files in a file systems, or maybe even just a box of paper index cards on a table. The next term, data model, is a little bit more abstract. In data management theory, a data model describes a formal definition on how data can be represented and which operations are available to modify it. There are many popular data models, both formal and informal, which are widely used. For example, a very basic data model could be defined for a physical index card in a wooden box. Data is being represented by writing it on an index card using a pen. Text which is already written cannot be erased, but can only be stricken through and amended with new text. This would be an operation to modify or not modify data. Cards then can be put into a box and then sequentially flipped through either from the front to back or back to front. A query operation. These are all operations which are available in this simplified data model. But of course, in the context of an AI system, computer-based data models are much more interesting than, data models for boxes and paper. And also here, many different variants ranging from representing data in semi-structured text to comma-separated lists, representing data using linked tables, or using complex network structures are available. We will have a look at some of these data models slightly later. The next term in our list is data schema. A schema defines the structure of one given specific database. This contrasts with the definition of a data model, which describes how data is represented in general, and not just for a particular instance. For example, let's assume that I want to create a student database. In the schema of that particular student database, I could define that I'm interested in storing data about students, where each student is identified by his or her student ID, and that I also want to store their first name, their last name, and their birth date. Such descriptions make up a database schema. Also, as a side note, people very commonly confuse these two terms and use data model and data schema interchangeably. But at least I try to be precise in this course in order to highlight the differences. Let's go through an extended example to understand these definitions better. Assume we want to create a music encyclopedia database in the style of musicbrains.org. In case you don't know musicbrains.org, it is an open source database covering music artists and their works and recordings. And here we see our informal definition at work. All the data in this database is related, so you will not store information about birds or cars in there. Instead, it will all be about music. And we will be defining a schema to ensure that all artists and recordings and so on are represented uniformly. And of course, as soon as we want to store this database on an actual computer system and power a website, we will need to decide on a data model and how to store that data and how to manipulate it. Finally, as MusicBrains is a website found in the internet, there needs to be a database management system installed to serve that website. Let us start by looking at the data schema, meaning the description of the structure of that particular database. In general, we care about two types of schemas: conceptual schemas and logical schemas. Let us start with a conceptual schema first. A conceptual schema describes all entity types and relationship types to be stored in a database from a conceptual perspective. But what are entity types? Well, informally, entity types are just different types of things. In the context of our database, an entity type could be artists, could be recordings, or could be events. Relationship types describe the possible relationships between different instances of these entity types. For example, an artist writes a song. These songs are then being recorded, resulting in a recording. These recordings are then collected in an album. These albums then are released on a medium such as a CD. During an event like a festival or concert, several songs are being performed by the artist. As you can see, defining such conceptual schemas can easily be done just using English language. It's not necessarily a technical or computer science activity. Instead, it's an activity which requires you to sit down and carefully think about what your database is going to store and which aspects of the domain, in this case artists and their songs and their recording, you're planning to store and maintain in that database. To some extent, this is an even somewhat philosophical task. And indeed, there is a subdiscipline of philosophy going back to even Aristoteles called ontology, which shares many of the same aspects as creating a data schema, just at a much grander scales. It's all these questions like, which are the things which do exist and how are they related? What makes a thing a thing? When does one thing become another thing? And big questions like that. Let us create a very simple graphical representation of the entity types for the conceptual schema we have in mind. We want to care about artists and their names, and maybe also an identifier to take care of multiple artists sharing the same name. For recordings, we also want to store an ID, a name, and also a rating describing how well that recording is being liked by people, and also the length of that recording in minutes. Finally, for an album, we want to store the ID, the name, and the release date. Now, looking at the relationship types. An artist records a recording. A recording belongs to an album, and an artist releases an album. Let's move forward to data models. As a reminder, data models are formal definitions of how to represent data in general and what operations are available to modify that data. I want to first start with the relational model due to its importance in the world of data management. The relational model is used by most of the large commercial and open source database management systems and is thus being deployed in a multitude of companies and websites. And it has been around for approximately 50 years. It is not the simplest data model, but it's also not the most complicated one. However, the core idea is surprisingly simple and can be summarized like this. Each entity type will be represented by a database table with rows and columns. Each table will have one or more columns representing the IDs of its rows. The feature which makes relational model particularly expressive is the ability to link several tables by referring to the ID of another table. Also, on top of these linked tables, the relational model defines a query language which allows us to create complex queries to retrieve data from multiple tables or even create complex statistics. Let's now check out logical schemas. Again, schemas define the structure of a specific database, and we have already created a conceptual schema for our music database, which we have in mind. The difference between a conceptual schema and a logical schema is that a logical schema takes a chosen data model under consideration. Now, suppose we want to choose a relational model which represents all data in linked tables. In that case, the question now is how to transform that English language informal description I had before for my music database and transform that into linked tables. There's a lot of theory for this task, and we can easily spend 2 full sessions in a bachelor course in this topic alone. However, in a nutshell, it's surprisingly simple. We create a table for each entity type with columns for each of the attributes we're interested in, and then decide which of these columns should be serving as an identifier or ID. Then we create a table for each of the relationship types and replicate the identifiers with the related entity types and links them. The linking is being realized by the concept of foreign keys, but we don't really need to go into details here. This results in a table structure which is being visualized by the diagram on the right. Well, this might sound a little bit abstract, so let's have a look on the actual table which will be stored in the database. On the left, we see the artist table, with all the names of all artists and an artificially created ID. On the right, we have a table representing the recordings with a recording name, the rating, and the length, and also an artificial ID. The interesting part, however, is that table in the middle, representing the relationship that an artist records a recording. You can see that this table contains existing IDs from both artists and recordings and links them together. I visualized some of these links here, and we can see that our artist with the ID 94, John Williams, is linked with recordings with the names like Superman Main Theme or Duel of Fates. It's rather simple, isn't it? Okay, to be fair, I just compressed 2 weeks of bachelor course into a few minutes, so of course there's a lot of details which I might have skipped, but we can already summarize some of the pros and cons of the relational model. The relational model is rather flexible and expressive, and you can represent all kinds of entity types and relationship types without too much effort. This model can also be flexibly used to answer queries. For example, by just following these visualized links here, I can easily find all recordings which belong to a specific artist. Furthermore, I can also focus on records first and easily find out for a given record which artist was the creator of that record. By the way, the more technical term for following these links is called joining tables, so I will use that in the future. I can also easily create simple statistics. So for example, I can go to the record table here, or recording table here, iterate over all recordings, and create a statistic about the average rating of all recordings or the average length of all recordings. And of course, I can combine statistics with joins and maybe some groupings, and then come up with an average record length for each individual artist. So for example, for John Williams, typical record length, 5 minutes. Another advantage is that the relational model is very well supported by database management systems, and these provide a wide variety of features and utilities. For any serious application, you want to have a proper database management system. But let's also look at the downsides of a relational model. To use it, you have to use a database management system. Yes, DBMSs are awesome, and in most proper applications, you want to have one anyway. However, maybe you simply want to store data and you don't really require all these features, and thus setting up a DBMS might be an unnecessary hassle. Furthermore, despite of what I said before, the relational model is actually kind of complex compared to many of the other more common, simpler models. And you need to design all tables for a database before you can actually use them. This can be a burden for many rapid prototyping applications. Let me stress rapid prototyping here, because I would argue that as soon as you make a serious application which is deployed for real and interacts a lot with its database, you should spend some effort on designing schemas to make sure that everything is the way it should be. Let's introduce a new data model, which we for now will call the single table model. This data model unsurprisingly, represents all data stored in the database in a single table. So one database, one table. This is obviously much simpler than using a collection of linked tables, but of course also much more restricting when it comes to expressivity. So why would we be interested in such a model? Well, because it is so simple. And it can also be very easily serialized into, well, a single file, like for example a comma-separated value file or an Excel file. I guess you all have seen either an Excel file or comma-separate value file before. An Excel file, for example, is typically just one big table. And yes, you can have multiple pages and technically thus have multiple tables in one file, but they're usually independent and not linked as we have seen in the relational model. In particular, Excel does not allow you to perform complex queries spanning and joining multiple tables. Nonetheless, there are many good use cases why you would want to use something as simple as a comma-separated value file or an Excel file, as for example for data exchange or for performing simple statistics or editing tasks. But how would we transform the conceptual schema we made for the music database before into something like an Excel sheet? This is not trivially possible, as the schema we created covered multiple entity types like artists and albums and recordings. How are we going to squeeze all of them into a single Excel sheet? Well, the answer, of course, is we are not going to do that. What we are going to do instead is we are adopting an aggregation perspective. So we think of a way how to aggregate the data from different entity types and relationship types into a single table. And there are multiple options for doing this. For example, I could say, hey, I'm only interested in artists and their recordings, and then come up with a single table which has the columns of artist ID, artist names, record IDs, record names, record ratings, and record lengths. Or I could be interested in artists and their albums. Or alternatively, maybe artists, their recordings, and their albums of that recording. But I need to choose an option here. I cannot have it all. For the sake of this example, let's adopt option 1. The resulting Excel file could look something like this. We have one row for each recording, and in each row we will find information about the recording itself, but also information about the artist who created that recording. By adopting this aggregation perspective, I unfortunately lost all information about albums. If I'm interested in albums, I then also need to create another Excel file which adopts a different aggregation perspective. What could I now do with this Excel file? Well, I can filter rows to find a specific recording or find all the recordings of an artist, but I cannot magically bring back the albums. Of course, instead of an Excel file, I could also create a comma-separated value file. While this file looks slightly different, it stores the same data and has the same operations available. So let's discuss the single table model a bit. As an advantage, it's extremely simple and data can be easily converted into files. These files then can be stored in the file system, and you do not really require a database management system to do so. On the downside, however, we need to adopt aggregation perspectives, therefore making it less flexible with respect to what we are going to store in these files. Also, there's a lot of redundancy. As you might have noticed in the screenshots on the previous slides, the information about the artist John Williams was repeated in every single row. So, if we now would want to perform a name change, we would need to change a lot of these rows, and it's very easy to mess this up, resulting in inconsistent data. One way around these restrictions imposed by just having one table would of course be creating multiple files, each of these files adapting a different aggregation perspective. However, that makes the problem of having redundant data even worse, as now we will have the same information and it can be found in multiple files repeated all over. For the last data model, let's have a brief glance at the document model, which is popular in many web-based applications in form of JSON or XML files. The core idea of the document model is to represent all its data in semi-structured text documents. To do so, we typically have to decide on one main entity type and then aggregate and embed all its related sub-entity types as substructures. The document model also defines several query concepts which are implemented in standardized query languages as, for example, XPath or XQuery. How would this look like? Again, we need to adopt an aggregation perspective, but can retain a bit of the entity type structure found in the conceptual schema. For example, we could focus on artists and then embed all of their recordings. Or, I guess we could also do it the other way around and start with the recordings and embed all artists. We could also adopt an option 2 here and focus on artists and their albums instead. Again, so many choices. Let's assume we go with option 3 and focus on recordings and embed all their albums. The resulting JSON file looks like shown on this screenshot. We have a list of recordings, not unlike a common separate value file, but the file is not flat. Each of the recording records has a list of albums and the recordings embedded. We can also see how this data model can easily have a lot of redundancy, as the Star Wars trilogy album information is repeated for every single record of that album. To conclude the document model, this model is still somewhat simple. It can also easily be converted into files, and some of the conceptual structure luckily remains. Also, I don't need to have a database management system in order to store JSON or XML files. I can do that in the file system quite fine. However, there are actually good document database management systems which will allow you to store and query XML and JSON files much more efficiently, like for example MongoDB or CouchDB. If you really have a lot of document files and care about accessing them efficiently, definitely check one of these systems out. On the downside, the document model is still a bit less flexible than the relational model, as it still forces you to adopt an aggregation perspective. So, queries joining several entity types are typically much harder to do in the document model than in the relational model. To summarize, what did we learn? Databases are collections of related data. Databases adopt a data model and are structured using a schema. The data model governs how data can be represented and manipulated. We addressed 3 data models: the relational model, the single table model, and the document model. The relational model represents data in tables which are linked to each other. The single table model represents data just in one single table. And in the document model, we have a hybrid between, and we use a semi-structured document. With this, I would like to thank you for your attention today and hopefully see you another time.